All right, so camera working. So this is easy now. The linear regression part was a difficult one, and you should definitely go through that yourself at home, I think. Now you can just relax, drink your Coke, and listen to the machine learning pipeline. We talk a bit now about not algorithms, but all the different things that need consideration when you do machine learning, and it's a lot. So this is probably, I just uploaded the slides, so I don't know if you take notes. The PDF is just in OneDrive since 2 minutes. So this is, I think, 120 slides. We will just do a few now and the next ones next week. So, linear regression. That's what we just talked about. Here's an example of linear regression. I mentioned already there's polynomial regression. So it would look like this. You as a machine learning engineer must make the decision what you want. Linear regression, polynomial regression of the second degree, or to the power of, like here's an example, to the power of 3, to the power of 6, to the power of 9, 12, and 15. So what do you think? You can get out your phones. See if the Mentimeter works. Which model would you choose if this data is what you have? Like always, go to menti.com, type in this number. So, as a future scientist, it depends. It's almost always the right answer. Also, as a politician, always depends. Who chose it depends? And what does it depend on? Yeah. What else does it depend on? Did you raise your hand?
So, ich hätte jetzt eigentlich vor Wege gesagt. Ich habe jetzt gesagt, wir haben gedacht, wenn jetzt nie wissen, was wir danach tun, wenn jetzt noch die Daten weiter strecken würde. Deswegen habe ich gesagt, okay, wir haben jetzt die gegebenen Sachen. Und man will es ja schon irgendwie anpassen, aber auch nicht zu sehr. Quasi. Deswegen habe ich gesagt, okay, eine Medien wäre mir zu wenig gewesen. Ich wollte es schon ein bisschen Form bringen, aber jetzt nicht zu sehr, das heißt, alle möglichen Tiefen, die es gibt, dass wir jetzt zu sehr die Form geht. Okay, mal ungefähr die Richtung, weil sehr nie perfekt sein kann.
So actually the right answer is, based on this data and information, you cannot say for sure what's the right model. But chances are that 15 is not the right answer, and probably also not 12 and 9. I am doubtful as well. And that's what we'll talk about later, again, overfitting and how you can avoid that and how you can test this. Chances are, but again, there's no proof of this. It's just experience and guessing. So whatever this data is, chances are there's some noise. So let's assume you are running, you want to predict how fast someone is running 100 meters. And you have a measurement of how much time does a normal person need for 100 meters? 13 seconds or whatever. Let's say 15 seconds to make it simple. And you measure the time. And probably maybe the time, maybe the person who took the time started a bit late or stopped a bit early, or the runner is in very good shape today, but he will be different tomorrow. So chances are next time the time will be a little bit different. And you can make a model like this that predicts almost every number perfectly. But chances are, just going back a bit larger, if you look at these data points here, I'm just guessing. Chances are that the next time you would make a prediction for this variable, whatever it is, the right prediction probably would be rather here than here. So normally having a smoother model will give you better results. Now, when you work with machine learning, there's 3 steps. First step is preparing everything. As part of that, you need to define the problem, and that is often not easy. It is easy here in the lectures, it is easy in the lab sessions. We always tell you, this is the problem, this is what you should predict with your machine learning algorithm. But if you work in a company, defining the problem is often, and like there's a business problem, and then defining that as a machine learning problem is often not easy. Same about understanding the data. Here in the lab sessions, you will be working with very small data sets, a few hundreds, a few thousand instances, a few dozens of attributes. Understanding that is easy. But if you work in a company, you have lots of data about customers. You have possibly millions of instances. You have thousands or tens of thousands of attributes, and making sense out of that, deciding which features to use for your machine learning model is not easy. Also about getting the data can be very challenging. Second phase is the learning phase. That's what you learn most about in this lecture series. That's about training and testing machine learning models, selecting algorithms, and that's what we talk about today, pre-processing the data. Important term, pre-processing means all the things you do before you train your algorithm. Yeah. So it includes cleaning the data, so removing data that you don't want, such as possibly some outliers or noise, dealing with missing values, transforming data, feature selection, many things more. And we will talk about each of these points briefly, maybe 5-10 minutes. To be really good in each of these points, probably would have, it would be possible to give an entire lecture about each of these points. And then the third part, which we will not be covering in this lecture series a lot, is really applying the model, deploying the model to production, monitoring the model, reporting to stakeholders. But of course, it's very important, but yeah, that's something for the future. There's many different ways of presenting this. That's just another way. Training and testing the model. Let's talk about that. And think about linear regression when we talk about that, not so much about KNN. So, what you will have as a student, or often as a researcher as well, is some offline data. Offline data refers to the standard tabular data set. All these examples we are looking at right now, the matrix or a table, tabular data. So you have your training data, and you try to build your model, like linear regression with gradient descent. You go through all your training data step by step with gradient descent and build your model. And you hope that once you have your model trained, you can apply that on new data in your production system. After some time, you maybe retrain your data. So this is your data set that you work in a company with, or here in the lab sessions as well. And the assumption is if this works well, if this model works well on this data, it will also work well on this data. But we don't have this data. So, and still we want to know as good as possible, how well will your model work on this data that we don't have? So the naive training and testing approach would be what we did in the past lectures. We just have all our data, the data points I showed to you, these simple examples of maybe 4 or 5 data points, and we train our model, we calculate for each instance how good it is, we sum it up and look how well it works. But that will lead to overfitting. It will, you will see that on one of the next slides. If you would use the entire data that you have in your data set for the training, so building your linear regression model, and then taking the same data to calculate the error, you will get a relatively good result. If you would apply that on new data, you could be almost 100% sure that your results would be much worse. Let's see. We should actually talk about this first. So what you actually will do or should do is one of the following things. The most simple one that is good enough in most cases is a holdout split, aka an XY split. So this is your data set, your whole data set, but you keep 20% or 10%, sometimes 30%. And you only use the remaining 70, 80, or 90% for the training. So you build your linear regression model on this blue training data in the way I showed to you, and then you evaluate it on the validation data. So this validation data was not used for the training. And you use this as an approximation of how well the model will perform on truly new data. You just take that as an approximation of the new data. So you take your whole data and you split it into your training data and your validation data. So imagine this is your full data set. So far, I always show to you, you should find a model that fits all of this data well, but that's not what you really do. You split the data and take out, for instance, randomly chosen the red dots here as your later validation data. So you have 2 data splits. This one you use for training, this one for validation. You build your model only on the upper blue data, and then take the same model and measure the errors on your validation data. And that would be the result you're reporting in a research paper or in your bachelor thesis. And it almost always will be worse. So this result almost always will be worse than this, because this model is optimized to be as good as possible here. But on new data, there will be some noise, some variations, so it will not be perfect, but that's how it is. And you can do that to optimize your hyperparameters as well. So maybe you would build your best possible linear regression model, but then you think, that's not really good. Let's try out polynomial regression, and you get this model. And you also try out an even higher degree of freedom. This would maybe perfectly model your data. It's an error of 0 or close to 0, but you apply it to your validation data, and then you would maybe think, okay, this one has the lowest error on the validation data. I will continue to use this model. Any question?
Gibt es da so mal, wann man sagen kann, ja, das habe ich Mobile Phone, der wahrscheinlich der Fehlerquote.
Yeah. So when is it good enough? That's what I said before. It really depends on what you want. It's good enough when the error does not change anymore, or if you just say that's good enough for my business use case. Yeah.
Irgendwas sehr viel Sinn dazu schreiben. Wir hatten jetzt eine Praktikum gehabt, wo wir Werte bekommen haben. Wir sagen, Maschine X mal gemacht werden. Wollen wir uns schnell Geld sparen, muss das alles planen, muss das will jetzt 10.000 Euro im Jahr sparen, das ist was.
Yeah. But it's really very subjective. There's no objective answer. It really depends on your business use case. So sometimes people confuse the different types of plots that you can have. This at the bottom shows a learning curve. That would be what you can expect if you train your linear regression model iteration after iteration. So this is the training time, and each time you adjust your parameters theta. So you should expect that on your training data, the error always improves and improves and improves until at some time it remains stable. You also would say it converges. So think of linear regression. Once you have the optimum, you stop your training, or even if you continue the training, the gradient is 0 or very, very small. So the updates are 0 or minimal. So your error remains the same. That is for training one model, let's say linear regression, with whatever hyperparameters you have chosen for linear regression or for KNN. Then there's hyperparameter optimization. That's what you see here. So think of KNN, what we had in the last lecture. You vary your case, and at some point you have the optimum. Like, you don't know how far you need to look. Maybe you start here, yeah, and you see accuracy goes up, 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 and then or rather what you would do is you specify the search space. So you say, I want to look at all cases between 1 and 100, or between 50 and 1000, and then you get this chart. But you never know what would happen if you continue K. Same with the degree of freedom, what we just had before. But actually, so with the degree of freedom, and that's again very important, if you look at the chart at your training data, the higher the degree of freedom, the lower your error will get. The higher the degree of freedom, the better you can model all your data. But if you then look at the validation data, at some point, the error will increase again. That's what you see here. So for instance, if this was an exam question, I would show this chart to you and I ask you, what do you think? Is this chart showing you the accuracy on the training or on the validation data? This would be clearly on the validation data because the error goes up again. But this is how you choose the degree of freedom. You would look at the validation data and look for the lowest, for the minimum here. This is not gradient descent. This is not where you can calculate somehow the minimum. This is a hyperparameter. You can only do try and error. Just try it out. Just try different degrees of freedom and look where is your performance on the validation data best. Right. So yeah, you would say here it has converged. That's good enough. Here you would then use the model, you would stop the training. Yeah. Okay, now let's go back here, the overfitting. I hope it gets more clear now that this would likely be a good fitting model, a model that is modeled like within a zigzag curve, modeling almost all data points perfectly, and then here going steeply down, that is highly likely to be overfitting. So we also say the model is not generalizing well. So you have your model, it's good on the training data, but the results do not generalize well to new unseen data. The solution to this, so if you observe overfitting, the solution would be a simpler model, maybe more training data, or maybe better training data. Yeah, same here. There's overfitting and there's also underfitting. Underfitting means it's too simple. So it's the opposite to overfitting. This is a linear model. As you see, it's not separating the data very well. This one would be quite good. And this one is overfitting again. So again, you will see this in the lab sessions. The typical training error always goes down. The validation error at some point has a minimum and goes up. And assuming that this is training time, you can just stop doing the training here. Of course, you don't know exactly, like again, you could have like small variations. It's always some fluctuations, so you need to define some threshold where you say, okay, if it's not improving that much, you would stop. If it's hyperparameter tuning, no, sorry. Yeah, for training time, you would expect the training error always to go down or remain stable at some point. For hyperparameters, the training error could also go up again. But the important thing for deciding what hyperparameters to choose is your validation error. Yep.
How should we know?
Stopping what? Training the model?
Some grades we stop and the grade is low, but after some grade we get the validation error and it goes up.
Yeah. Again, it depends on what we are talking about training a model or looking at the hyperparameters. Looking at the hyperparameters, so like what K to choose or which degree of freedom to choose for the polynomial regression model. You define the search space first. You define, I want to look at K between 5 and 100, or I want to look at a polynomial degree between 1 and 10. And then you would not really look at how it develops. You would have this chart and look at it, or your program just takes the lowest value. If we talk about training a model, so let's say you know already, like training a linear regression model, you would again have to define when you want to stop after a certain amount of time, just because you don't have more time, or when the error does not improve anymore, notably, like if it just fluctuates at a low level. Maybe talk about that more in the lab sessions, or just try it out. Look at what happens and then see this. Typically better solution, no, not really typically better, it depends. An alternative to a holdout split is k-fold cross-validation. In k-fold cross-validation, you split your data sets into k-folds. Don't confuse this with k and n, it has nothing to do with each other. So you choose a k, again, just typically maybe 5 or 10, that's the most common chosen values. You have all your data, you split it into k folds, let's say 5. Then you use 4 folds for training and 1 for validation. Then you repeat your experiments on other, so you choose a different fold for validation and use the remaining other 4 for training. And you use again then another fold for validation and the other one for training. So you repeat your experiments k times, 5 times, for instance. The advantage here is this is especially good for smaller data sets because you ensure that every data point, every instance in your data set is used at least once for the training. Now, if you use the holdout split, 20% of your data is never used for the training. If you are unlucky, some of these data points are very important. Typically, the difference between k-fold cross-validation and holdout is not huge, but you see on one of the next slides how big the differences could be. The disadvantage, of course, is your runtime increases by a factor of 5 or 10. On the small data sets, it doesn't matter. It doesn't matter if it's 5 seconds or 25 seconds typically, but if it's 1 day or 5 days, that could make a difference. Or 1 week or 5 weeks, and definitely 1 month or 5 months could make a huge difference for your bachelor thesis if you only have 4 months time. That's an example how it looks like for k-fold cross-validation. So they looked at hyperparameter optimization to find the optimal k on some data set. And here's the accuracy. So accuracy is between 24% and 32%. And you see for each k 5 data points. Let's look at this one. So for k roughly equaling 50, in the first or in one of the 5 runs, you got this accuracy. In another run, this accuracy, and this, and this, and this. And basically each of these runs is like one run of a holdout split. So if you decide to do one holdout split, you also separate your data to 2080. And it would be pure chance if you get this result, or this result, or this result. Or maybe, who knows, even this here result. And you see it is quite a difference. It's between 29% and maybe 26% accuracy. So 3 percentage points difference. Or if there's some even larger discrepancies like here, 27 and 31. So 4 points. And by using cross-fold validation, so you run it 5 times or 10 times and build the average. That's the blue line. And that's giving you, so it could be, well, I can't paint here, but if you're very unlucky, let me think. If you do just a holdout split, maybe your first k, you would get this result, like the highest possible of those 5. The next k, maybe this one, so the lowest possible, again the lowest possible, again the lowest possible, maybe then you jump here, and then here again. So you would have a very strong zigzag line. Even with k-fold cross-validation, you see here, it's a little bit zigzag. So yeah, the optimal k is somewhere here. But by repeating it with small data sets, k times, you get more reliable results. Call in user. That's interesting. Huh? It's gone. So this is all, it's not set in stone. It's like just rough guidelines. You potentially can expect somewhat lower errors with k-fold cross-validation. It gives you a better estimate of what you can expect on the future unseen data. There's two, this is sometimes in the exam, it's very simple. There's two ways of averaging the folds. So if you do k-fold cross-validation, you can either calculate your metric. So we didn't talk about these. Accuracy, we talked about, this could be root mean square error as well. You do it for each fold here and then build the overall average. Or you calculate, actually, we have not yet covered what this means, true positives, true negatives, false negatives. So look at this maybe again after this lecture once we have covered that. But this is basically how many instances were classified correctly. And you can do that for all the folds and then calculate that. Like here, 10 of these were correctly classified, 8 of these, 1 for this, 1 this, and build the average. And sometimes, like for this metric, precision, it depends how you calculate the average. You get slightly different results. In practice, it doesn't matter. Just be aware that there's two ways of calculating it. Cross-validation, like I said, each of these points I talked about now for 5 minutes. You could write a PhD thesis about that. Some people have. This is a good overview paper if you want to learn more about cross-validation. It's 9 pages with more details and also alternatives. And there's many other things like leave one out, cross-validation, bootstrapping, and other variations. There's one more data set that you can use, or one split that sometimes is useful. It's called the test set. Actually, also sometimes validation set and test set is used interchangeably or like differently. If people talk about test set and validation set, always be sure you understand what they mean. So, because even if you use k-fold cross-validation or a holdout split, it can happen that you are overfitting to the validation data. So look at this example again. This is your full data set with the true but unknown optimal function. You take this for the validation data, you do your iterations, and you find your optimal model on your validation data. It's still not where your true unknown model is. If you have an additional test data set, it increases the chance that you have a meaningful result that is representing your future data as good as possible. So what you do, and this is what you should do always, you should always have a test set. It doesn't matter so much if you use holdout or k-fold cross-validation, but you must have the test set in your, when you do a bachelor or master thesis and you do machine learning experiments. You have your whole data set. You split it into training and validation or k-fold cross-validation. But before you do anything of this, you take your test set out, a small number, like 10% of your data, maybe, and you put it aside and you do not look at it. And then you do all your experiments with your training and validation data. And you can do all the things I'm going to show to you in this lecture. Remove outliers, change the features, whatever you want to increase the performance. And when you believe you are finished, you take your model that you have trained and that performs best on the validation data, and you evaluate your model on the test data. That is what you report in your thesis, in your research paper, or to your boss in a company. That is the best guess you can have how your model will perform on the true future data, also sometimes called out of sample data. Again, this data, you just don't have it. The reason why you do this, it's sometimes not so intuitive, but you are using the validation data to still fit your model. If you optimize your hyperparameters, you choose a K that is best on the validation data. But there is noise in your data. You can be 100% sure that whatever is best here is not necessarily best here or here. Is that clear? Even if the intuition is not 100% clear, trust me on this and just do it. Yeah. The error on your future data is potentially always larger than anything you have in your experiments, because data changes over time. So if you have collected data over the past 5 years, and then the data is lying around for 1 year and you do your experiments, the user behavior, the items, whatever, have changed compared to what you will use in the future. And yeah, so I plotted here like a line for the test error, also the error on the future data. That is purely hypothetical. You never know this because you are not evaluating your model during the development phase on the test data. Yeah. So you only work with training and validation data, and at the very end, your test data. Yeah. Also quite important, but we are not going to much detail here, is typically when you work in a business, you have huge amounts of data. You use typically not all of that for training. You just use a sample of this, and there's different sampling strategies. The bias variance trade-off is just referring to underfitting and overfitting. So it's just two terms you should be familiar with: bias and variance. So a high bias occurs when an algorithm has not enough flexibility. You could imagine, like, think of the real world, like you sometimes say people have bias, they maybe have stereotypes, they are so fixed in their brain, they are not able to differentiate between different things. They just have their opinion and it's fixed. They have a bias. So it's not flexible enough. On the other hand, if something like a model has a high variance, it means it's very sensitive to different training data. So the advantage of a person, a human with bias, the advantage is it's quite a stable prediction. This person will always make similar or the same prediction about certain other humans with a bias. The same about a machine learning model. If it has high bias, it means it's underfitting. It's like a linear model. It's very predictable what the output will be. It's not changing a lot if you change the data a little bit. If you have a high degree of freedom, your model is overfitting. And if you change the data a little bit, if you have one more outlier, your model changes dramatically. Now, if, let's say you have a linear regression line like this, and the data points are everywhere here. And then you have one outlier here. Maybe your model changes a little bit like this. If you have a curve like this, and then you have one new outlier, your curve will change like this. Then you would say you have a high variance, and you want to find that point where the bias variance trade-off is the lowest in the middle. It's just, like I said before, where your test data, or more precise. So here they use the word test sample. That's what I before described as the validation data is lowest. Did you have a question? Yeah. No. Bias does not describe that you have not had enough iterations. It describes that your model is not flexible enough to model all the data points. It's just basically a different word for it's underfitting. If it's underfitting, like a linear model for data points that are like distributed like this is not good. This is, by the way, interesting because this is like they've repeated the same experiments many, many, many times. And you see like here all the red, like the light red curves are different runs, and then the bold red curve is the average, and you see that there's quite a big difference. Yeah, so here's low bias, high variance, so the model complexity is high. Here's the opposite, high bias and low variance. What do you think? What's the training curve? What's the validation data? Yeah. Yeah, correct. I would assume so. Overfitting is a real problem, and it happens to many people. A few years ago, when I was giving this lecture, I was, as part of this lecture, doing a Kaggle competition. A Kaggle competition is something where I upload a data set, and then all the students download a part of it, like the public part. They create their model, and then they make predictions for the private data set without knowing what the right answers are. And you see here the ranking of the students. And you see here the ranking on the private data compared to the public data that the students trained on. And what you see here is that this student is 18 ranks lower than on the public data. Here, this one's 14 ranks lower compared to other students where it maybe varies just 1 or 4 or 2. That's what is to expect. If you, like, if all of you were to train the linear model, the camera's not moving. All of you train the model on the same data, you would all still get slightly different models based on how you split your data, for instance, based on the hyperparameters you choose. And if you then, and one of you would be the best, and the other one would be second best. And if you then use the same model on some other data, it's to expect that there are slight differences. Maybe the first person is then second, but you would not expect that the person who's best on the public data is maybe last on the private data. If this happens, like it happened here, then it means something was gone wrong in the training, and very likely the reason is overfitting. Now we go through this quickly. That is what we had already. All these charts I showed you in the first lecture. If you someday, I mean, now in the lab sessions, we always tell you, do this algorithm, do this data set. If at some day you need to make this decision yourself, these things can help you for a first impression, and also to see what algorithms are out there. But algorithm selection, that's something I would like to talk about, that's actually one of my main fields of research. Algorithm selection is extremely difficult. To identify the best algorithm for a given scenario is very different. And this is true for machine learning, but this is especially true for recommender systems. That's my primary field of research, so recommendations. We also use machine learning, but we also use simple algorithms like Most Popular, where you all know this from Netflix or Spotify, where you just get recommendations for those movies that are most popular in Germany or on Netflix in general. So there's different types of algorithms, machine learning and non-machine learning. And if you want to build a recommender system or any machine learning system, then it is very difficult to decide which algorithm to choose. This is an experiment that we did some years ago. we used 5 different algorithms. It doesn't really matter what these algorithms are, and applied them on 6 different news websites, German news websites. That's the Kölner Stadtanzeiger, that's a sport news magazine, Motor Talk, that's some business, I think, I'm not sure, about technology and politics. And what our expectation was, at least in the beginning, was that algorithms should perform similar, not identical, but we would assume an algorithm that performs well on a German local news website like Kölner Stadtanzeiger should also perform reasonably well on other news websites. Eventually, it's all new German news websites. But this assumption was completely wrong. So as you see here, the metric is precision, the higher, better. The algorithms are completely different. Like, look at the orange one, that is most popular. That work very poorly on this website, but best on this website. If you look at this algorithm, that's the first one here, user-based collaborative filtering. Works best on Kölner Stadtanzeiger, but let's find website, but yeah, like average on here and here. So on every website, a different algorithm performs best. That's a big problem. If you work in a company and you want to create a recommender system, which algorithm do you choose? And I can tell you there's not only 5 recommendation algorithms out there. There's dozens or hundreds. So which one do you choose? The answer is, unfortunately, you must try them out. All of them, basically. Or the more you try, the more likely you get a good algorithm. And that, of course, is not feasible for most businesses. Maybe if you're Google, you can implement 100 algorithms and test them, or 1,000 and test them in your production system. But in a small or medium-sized company, you can't do that. And it gets even worse. So we were looking at one website, I think it was, I forgot which one it was. I gesture with my hands, the camera always loses track of me. So this is the results of one of the websites at different times of the day. And what you see is that starting at 4 o'clock, this blue-white algorithm, that's the most popular sequence algorithm, is best. Here it's best, here it's best, here, here. So throughout the evening and the night, until the early morning hours, until 4 o'clock. And then between 4 in the morning and 4 in the afternoon, the orange algorithm is best. Here, 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 here. So what does that mean? It means you should use algorithm 1 in the evening and late hours, and another algorithm during the day. Unfortunately, this was not the only variable. If you look at other things like which device people use, the mobile device or computer, even things like gender or age, always different algorithms perform differently well. So if you want to have really the very best algorithm, you would have to deploy multiple algorithms. So this can become increasingly complex. And unfortunately, there's not in German die eierlegende Wollmilchsau for algorithms. This is true in machine learning and recommender systems. You cannot have this. You cannot have the one algorithm that can do everything. That's the reason why, if you use Netflix, you have all these columns. You have recommendations that are most popular, even there's variations. Most popular on Netflix, most popular in your region, so your country, most popular in the last week. And then they have movie recommendations because you like that movie, and movie recommendations because you like this movie, and so on. I mean, it's not really ideal. If Netflix, which is a multi-million company, you would expect they should be actually give maybe just show me 2 or 3 movies, right? And one of them should be like a really good recommendation. But instead they show you dozens of movies. And often actually, personally, I don't like the recommendations so much on Netflix. And that even though Netflix, I think they have 100 engineers working on the UI and the recommender system. Yeah, so there's not one algorithm that can do everything. The same is true for ChatGPT. I mean, the community is working, like ChatGPT is great for text, and you can use ChatGPT to create images, but still it's not the same model that is used for creating text. I think they're trying to somehow develop something that can do both, but it's just really just different ways to create text and images so far. The same is true for recommendations and everything else. Now, so much about the training procedure, like testing and splitting the data. Another important step is the pre-processing. So what do you do with your attributes, your features in the data set? So what can go wrong with data? Let's make this a bit more interactive. If you work in a company and you have data sets, what can go wrong? You mentioned already in the very beginning outliers, right? I think. Was noch? Sie haben Ausreißer erwähnt.
Vielleicht Daten, die Lücken.
Yeah, you can have missing data, gaps, something that is not there, even though it should be. What else?
False data, or maybe data statt integer float or
Incorrect data, like just completely incorrect or the wrong data format. Yeah, many things. So dirty data that you need to clean somehow, missing data. Very important, feature selection. We now always look at these very simple examples of 1 or 2 features, but realistically, you have dozens, hundreds, or thousands of features that maybe are not all important. Maybe you want to reduce features, combine features into one feature, or completely create new features by adding data from third-party sources. And very important, very often you need to transform your data so that you can use it with your particular machine learning model and scale it. In machine learning, we have the nice saying of garbage in, garbage out. So if you put something bad into a machine learning model, you will get something bad out. And this goes 2 ways. You can have bad data, but even with a perfect model, you still get garbage results. You can have perfect data, but with a badly trained model or just an unsuitable model, you will still get garbage results. So both data and model must be reasonably good to get good results. Let's talk about the first thing, feature selection. How do you know which features to select? We use study time and average marks in our examples. How about row ID and student ID? Should you include that? Yeah.
Doesn't matter what ID. It's better on this table how much I stay and how many marks I get.
So you think that you cannot get any useful information out of the IDs to make a prediction for the salary? Any other opinions? This is completely useless without any information, the row ID or the student ID. Is the student ID not telling you something? Yeah. Just forget this about a moment. think of Siegen, the student ID. Can you not see anything if you compare two student IDs? What does it tell you?
Das Zeit jetzt schon hier.
Ja.
Erstmal, aber wenn die Jahrgänge Probleme haben mit bestimmten Themen, mit bestimmten Arten, wie gelehrt wird, dass man da vielleicht schon, dass man sagt, okay, vielleicht vor 2 Jahren haben wir Scheiße gebaut, jetzt ist es besser geworden.
Yeah, you can definitely infer from the student ID how long a student is enrolled at the university. Lower IDs mean they are enrolled since a longer time, because the student IDs are incremental. And maybe not here in the example, but the row ID typically should have a perfect correlation with the student ID. Normally, if you have maybe a register of students, normally it would be sorted maybe by, like, you know, you put one up after the other. So there's a chance, at least, that the row ID also tells you when a student enrolled or when a student was added to the database. So you should never actually just use common, like what you believe, like logical reasoning or common sense to decide what features to use. You will be surprised how often features that appear useful are not useful, and the other way around. You mentioned already correlation. That's a good point. So there's different ways of deciding what features to use. Correlation is the most simple one. So you can look at, first of all, how the variables correlate with each other. If two attributes correlate highly with each other, then it's sufficient to, in a tendency, it's sufficient to just use one of them. It has the advantage training is faster. Yeah? In general, the less attributes you have, the better. The smaller your model, the faster the training, the faster your calculations in the end. But of course, also typically, the more features you have, the better you can make a prediction if all features are independent of each other. So correlation between features, and most importantly, correlation between the features and the label. If a feature has a high correlation with the label, very likely the machine learning model can get some information out of it to make prediction. This is just a heat map that shows you the correlation between different features. Now, correlation is not really something that you can do very well automatically, and then you need to decide what the threshold for correlation that you want to use to include a feature. So that's not really so much used. It's more commonly used to use a wrapper method, and that's very similar to the hill climbing that I showed to you in the beginning, but even simpler. So you can do forward feature selection, meaning you just start with, well, not really, well, with 0 features or with 1 feature, should be 1 feature. So you train a model for each of your features individually. Look which of these models is best, each trained only on one of your features. Then you take that best model or that best feature and add one of all the remaining features to it. So you train that again, many models with 2 features each, the one single best that you found and one of the remaining ones. That's exactly the hill climbing approach from the first lecture of the PICE, if you remember. And you just look how long performance increase. So like that's what you would see here. So you would stop here. I have no idea why this happens, but normally then you would stop here and use this number of features. You can also do the other way around. So you start with all features and then just remove the worst performing feature. It's a bit problematic as such that it uses, again, a lot of computation. Think about it. This is just feature selection. You also want to do maybe hyperparameter optimization, so optimize the degree of freedom. So you would have to do feature selection combined with each degree of freedom. You decide you want polynomial regression. You want to try out all degrees of freedom between 1 and 100. So that's 100 runs. That's no problem, 100. But then each of these 100 runs, to get the best performance, you should do feature selection. And there's many more things, as you will see, that is coming. So this becomes exponentially expensive. So eventually you have to make some decisions sometimes. Yeah. It's not always the case that the more features, the better. The more features, the more complex your model must be. Thinking of linear regression, the more xi you have, the larger your parameter space. This is so there's many different feature selection methods. You don't need to memorize this. Just if one day you really need this, have a look here. And then again, if you look for machine learning and feature selection on Google Scholar, you find tens of thousands of research articles. They all try to give you the best feature selection method. So don't ask me what is the best way to identify features. Each software library gives you typically a small number of functions, and there's not the one best answer to that. Data cleaning, that's a very annoying but useful and necessary task. And there's different types that require cleaning. The first one is noise. And noise can have many reasons and many ways. Noise basically means that's what you said before, it's incorrect data. Not necessarily completely wrong, but wrong to a certain degree. And it can affect both. The attributes can have noise, but also the labels can have noise. There's stochastic noise, which is random. So if someone measures your temperature or your body weight, it always varies a little bit based on the day. I don't know when you are lightest. Anyway. Then there's human error, sometimes doing intentionally. Human error just to save time. Maybe a nurse is under distress, very stressful conditions in the hospital to work, and then the nurse wants to save time. And the nurse is not measuring the temperature of the patients every day. Maybe the nurse is just writing down the temperature from the previous measure. So the nurse measures just every second time for real. Something like this. Humans are lazy and they find ways to cheat sometimes. So this is human error. There's systematic noise, like a poorly calibrated thermometer, where all your measurements are wrong in one direction. Really annoying if you work with web development. Then something like web crawlers or bots will introduce a lot of noise. I experienced that a while ago. I developed a recommender system for a website. It was a recommender system as a service. So other website could request from my API recommendations. We would deliver the recommendations. They were displayed on those partners' websites, and we were monitoring how often the recommendations were clicked. And we were assuming the more often the recommendation is clicked, the better the recommender system works. Unfortunately, search engines like Google and many other bots are crawling the web, spammers, search engines, and they just follow all links. So we very often, in the beginning, we're very happy. We thought, oh, someone had clicked all recommendations. Amazing, we give really good recommendations. But of course, it was false. And because just some robots followed all recommendations. And that introduces noise. It's useless. It's complete useless data for us. Yeah, the solution, of course, either you delete the data or you correct the data if you are able to identify it, which often is just not possible. That's a really crazy example of, not in computer science, but in biology, what noise can look like. So some lab, some research group, they did experiments, they published the results, and then some other research group could not reproduce the results. So they got completely different results. Some lab mouse tests, I think, for some drugs probably. And the reason was that the mouse reacted differently to different genders. So they were more stressed through the smell of human males than human females. So if you had a lab, a research laboratory with many men, and you had a lab with many women, you got different results in your experiments. So this introduced noise to your data. And yeah, who would be thinking of this? If this is introducing noise, what else is introducing noise that you are not thinking of? And you maybe have heard of that science is in a reproducibility crisis. So researchers like me, we publish something. In computer science is still not so bad, I think, but like in medicine, researchers publish something and other research groups try to replicate the results, but they can't do it. So they get different results. And that's a problem. If I say this drug cures cancer, and then someone else is doing the same experiments and they find this drug is not curing cancer, what do you do? Yeah. This is often caused by noise. Also, it's also caused by misconduct of researchers or by laziness, but also by things like this. And then there's outliers. So this is made up data. Yeah? It's not real data, it's just to illustrate the point. Let's assume this is real. Camera is off again. Should use less gestures. So let's assume this is the year. This is the temperature of the year measured. What about this? Is this noise and or an outlier? Outlier and noise, or only an outlier, or outlier and noise, or only noise? So if you think, let's talk about outlier. What if the data point was here? Still an outlier? ChatGPT is waiting the lobby. Let's let ChatGPT in. Hello, ChatGPT, we were waiting for you. So if it was here, was it still an outlier? It depends. It depends how we define outliers. We talk about that later. Yeah, it is probably an outlier. Is it noise? Yeah. So it's either or it could be both. How do we know if it's noise or not? We can't know for sure. For an outlier, I will show you later methods to determine if it's an outlier or not. And very likely it would be identified as an outlier. For noise, we don't know. Noise means it's incorrect data. So how do you know if this is incorrect? You don't know, as long as you don't have more information, as long as you would not have lived in 1994. So that's where most of you were not born, probably. Or if you had measured this yourself, or if you could look at least at the raw data and maybe you would find some information if this is correct or incorrect. So you don't know if this is noise. You know it's an outlier, probably. You don't know if it's noise. Here it's very likely an outlier, depending on the methods you use, and also very likely noise, but you don't know for sure. Outlier detection, and then how you treat them, has a significant effect on your model performance. This shows you just an example of a linear model. So the orange points here are the data points, and then the blue line is the linear model. This is the original data. And then, if you say that these are outliers and you remove them, you end up with this linear model. That's massively different. And to make this a bit more specific, there's different ways of removing outliers. So you see here's RMSE, so large errors are being punished. If you use the original data with outliers, you have an RMSE of, whatever data set that is, of 0.93. And then you see different outlier methods, and the performance becomes much, much better. Yeah? RMSE, the lower, the better. You will see on the next slides what this means, Windsor ring removal. But so here you are kind of changing the values. Here you remove it, and here you transform normally all data points. So you take the log of all data. And that's much better, right? 0.93 versus here 0.18. But then if you did take a different algorithm, so this is linear regression, this is random forest, you use the same outlier detection methods. And you see that with the outliers, the performance is among the best. Log transformation, again, is slightly better than this, but like not notably. So we have another problem here. How do you treat outliers? The answer is it depends. I cannot tell you use this method. It is best for treating outliers, like removing them or transforming them or normalizing them. It depends on the algorithm. It depends on the data. So the only solution, again, if you want to have the best possible output, try them all out. The general problem about outlier detection is that normally you focus on a single attribute. It's quite possible that attributes correlate with each other and depend on each other. So you would get better results looking at different attributes at the same time, but that's beyond the scope of this lecture. Now, one task for you, it's the last one for today, then we stop, read the slide. Also, the image I created with ChatGPT, quite good, I have to say, I think. So that's your homework. Read this. We talk about that in the next lecture. Read this, think about the questions. That concludes today's lecture. Thank you very much. I see you, I think, next week or in 2 weeks? Next week, right? Next week is 1st of May. Yeah, so I see you in 2 weeks. Thank you. Yes, you can.